blow it up. Hmm. Yes, I'll reopen section 1.4. It's not going to be due this week though. It's going to be due next week. Okay. Yeah, yeah. So, or rather, it's not going to be due this upcoming Sunday, but the following Sunday after that. Okay. Yeah. So sorry that my calendar that I created at the beginning of this semester, the due dates on those no longer correspond to what we're doing, but we'll catch up to that. So, yeah, and at some point I'll be like, okay, now we've caught up to the calendar. Okay. Yeah. So we'll get there though. All right. So section 1.4 is on complex numbers. Okay, complex numbers. Okay, and so in a high school algebra course, right, you probably talked about square roots of negative numbers. So you've seen the imaginary unit I before, right? We're going to basically be covering all of that in a single section, right? So here we go. Our subheading here, the imaginary unit I. Okay. All right. So I'm going to call this thing a definition. Okay. And it's also kind of like a note or a remark as well. Notice that a squared is greater than or equal to 0, right? For all real numbers a, right? Enough. Now, when we say that the square root of b is equal to a, right? Yeah, so when we have an equation like that, when we're solving like square root of 4, we say that it's equal to 2, right? This means that a is a real number such that a squared is equal to b, right? It's a number that when we multiply it by itself, we get b, basically, right? So that's what it means when we're taking the square root of something, right? Okay. Any questions on that, or is that fairly obvious? Yeah. Like square root of 9 is equal to 3 because 3 squared is equal to 9, right? Yeah, so they're identical statements, basically. Yeah. Okay. Right. So we have that any real number, when we square it, right, we're going to get something that's non-negative, right? Could be 0, right? Because 0 squared is 0, right? Yeah. But then any other real number we plug in, whether it's positive or negative, if we square it, we get something that's strictly positive, right? So like -5. If I square that, that's -5 times -5, which is positive 25, right? Yeah. Okay. So having that then, um, I'll say hence, which is just another way of saying then, or since, or rather not hence, since, but therefore, right? So hence, square root of b is undefined in the real numbers. For any b that's negative, right? Any b that's less than 0, square root of b would be undefined in the real numbers. We can't take the square root of it. It's like probably what we usually say, right? We can only take the square root of non-negative numbers, right? Okay. I bet if I close this door, maybe it won't be so jarring. Okay, so we can't take the square root of negative numbers. Okay. Well, it turns out we can take the square root of negative numbers. It just won't be a real number. Okay. So it's undefined in the real number, sure. So here's what we're gonna do. We define I, or sorry, I'll say we'll define the imaginary unit. Imaginary, I cannot spell today. Imaginary unit I to be equal to the square root of -1. Okay. Yeah, so we're gonna define that I is the square root of -1 now. Okay. So I'm gonna write that over here. I is the square root of -1, which is equivalent to saying that I squared will be equal to -1, right? If we multiply I by itself, it should be equal to the thing under the radical, right? Yeah. Fair enough. So I equals the square root of -1, so then I squared equals -1. Okay. Any questions on that? That didn't help at all. So that, all right, so the reason that we're doing this, we may use I to simplify square roots of negative numbers. Square roots of negative numbers. Okay. And I'll give an example of this. Yeah. First, I'll pause here because I want everybody to write that down. So, okay. So now, right, let's do an example. I'm going to scroll up a little bit. Okay. This is good. Yeah. Okay. So now, example here. Let's do the square root of -25, right? Okay. Now, I'm going to use the fact here. So maybe I should have a fact over here on the side, right? That the square root of a times b, right? So if I have a times b, just two numbers, a and b, right? That's going to be equal to the square root of a times the square root of b. In other words, square roots distribute over products. Yeah. Same thing with division. If we have square root of a divided by b, that will be equal to the square root of a divided by the square root of b. Distributes over quotients as well. Okay, fair enough. So that's nice. That's a nice thing about square roots. And not just square roots, but raising things to any power, really. Yeah, we have that distributes over products and quotients. However, if we have the square root of a plus b, that is not the same thing as square root of a plus the square root of b. Same thing with differences, right? That is not going to be the square root of a minus the square root of b. Okay, I just want to point that out because, well, this is a really common mistake I'll see on exams is that they'll try to distribute square roots over sums and differences. Okay, so don't do that. Yeah, they only distribute over products and quotients. Okay, fair enough. All right, so now that I have that, now let's do this example, right? I'm going to re-express -25 as 25 times -1. Okay. Okay. And now that I've done that, I can use this fact to say, oh, well, that's just the square root of 25 times the square root of -1, right? Distribute that square root over the product. Now, we already know the square root of 25 is just 5, right? And we're defining the square root of -1 to be I. So it's just 5 times I. Okay. So the square root of -25 is 5 times I. Okay. Any questions on that? Any questions at all on that? Okay. All right, good. So now that I have how we're going to be using this I here, let's do another definition. Okay. The set of all numbers of the form a plus bi, right? For some real numbers, a and b. Okay. So a and b are both real numbers. Okay. Yeah, and then a plus b times I, right, is the form of the numbers that we're actually looking at, right? So the set of all such numbers is called the set of complex numbers. Complex numbers. Okay. Okay. Moreover, right? And a plus bi is called the standard form. of the complex number. Why do I make that distinction? So the reason that I'm making that distinction there, that it's called the standard form of the complex number, is because we can express complex numbers in other forms as well. Like there's a really nice form called polar form, which we use in trigonometry quite a bit, right? And so, so yeah, we could express it that way, right? And so, standard form is what we're going to be talking about in this class, though. Okay, so a plus bi, right? Okay, couple more definitions here. Add it to the same set here. Okay, the real number a is called the real part of a plus bi. All right, so it's the real part of the complex number. Okay, the reason it's the real part is because there's no I attached to it, right? So that's just a real number, a right there. Okay, and we'll write this. The real part of a plus bi is equal to a, right? So that's just standard notation there. Okay, sometimes I'll spell out real, real part of a plus bi. I usually abbreviate it re, right? Okay. Fair enough. So it's a function. We're plugging in a complex number, and the output of that function is just the real part, a. Okay. Yeah. Okay, so good. So that's the real part, okay? And I'll say this. And B is called the imaginary part. Okay? Not B times I. Yeah, just B, right? So that's kind of confusing. So basically, the imaginary part of a complex number is just the real number that's being multiplied by I, right? Fair enough. Just the real number part of it. Okay. Fair enough. So we have a notation for that as well, usually abbreviated IM of A plus BI, and that's going to be equal to B. Okay. Just B. Okay. So whether you're looking at the real part or the imaginary part of a complex number, you always get a real number out. Okay. Fair enough. Okay. Now let's talk about some special cases here. If B equals 0, right? So it's just a special case of a complex number. If b equals 0, then our complex number simplifies, right? A plus bi will then be equal to a plus 0 times I. 0 times anything is just 0, so we have a plus 0 will just be equal to a, right? So your complex number is just a real number. Just a real number, right? So basically, if your imaginary part is 0, then you're a real number. Okay, fair enough. Kind of rewrite this word here. Just. Any questions on that? Okay. Okay. If a is equal to 0, okay, then, right, your a plus bi here. Well, now that a is 0, you have 0 plus b times I, but 0 plus anything is just itself, right? So we just have b times I, right? It's just a real number times I, right? And this is called a purely imaginary number or a pure imaginary number, depending on the textbook. So I'm going to call it a pure imaginary number. So your complex number is just pure imaginary because it's being multiplied by I, right? Okay. So any questions on that? Those definitions there? All right, so with real numbers, it's easy to say when real numbers are equal to each other, right? 2 is equal to 2, 3 is equal to 3, and so on and so forth. What does it mean for a complex number to be equal to another complex number? Well, it's pretty much the same. So equality of complex numbers, right? So let's let Z1 and Z2 be two complex numbers. Okay. Yeah, and I could write them in standard form if I wanted to. Yeah, so Z1 could be A1 plus B1 times I. Z2 could be A2 plus B2 times I, right? Could do that, right? So let Z1 and Z2 just be two complex numbers. Z1 equals Z2 if and only if, which means the only way that they can be equal to each other is if the real part of Z1 equals the real part of Z2, and the imaginary part of Z1 is equal to the imaginary part of Z2. Okay? So that's the only way that two complex numbers can be equal to each other. Their real parts have to be the same, and their imaginary parts have to be the same. Okay? Fair enough. So I can rephrase it in terms of standard form. So let's suppose Z1 is A1 plus B1I, and Z2 equals A2 plus B2I. So then restated, this means that Z1 will be equal to Z2 if and only if A1 is equal to A2 and B1 is equal to B2. Okay. All right, so any questions on that? On the equality of complex numbers? Any questions on that at all? All right, so that's some background on complex numbers. Now we're going to talk about how we can do algebra with complex numbers, right? So we have to talk about operations on complex numbers. Okay, scroll up a little bit here. So the next subheading here, operations on complex numbers. Okay. Okay. So we're going to start with adding and subtracting. Okay, so adding and subtracting. So let's say I have two complex numbers. Well, let's do it in standard form. So suppose I have A plus BI plus C plus DI. Okay, fair enough. So that's just two complex numbers and we're adding them together, right? Well, parentheses don't matter because addition is associative, right? We can add them in any order we want. So this is really the same thing as A plus BI plus C plus DI, right? Okay. Now, right, this is the same thing as A plus C plus BI plus DI, right? So I kind of have my real parts on the left there, my imaginary parts on the right. Yeah, and I can do that because addition is commutative, right? Fair enough. Something plus something is the same thing as reversing, right? Yeah. Okay, so now that I have that, right? Well, A plus C is a real number, so that's great. And then BI plus DI, that's like purely imaginary there. Both of them have an I in it, so I can factor an I out of that, and I get plus B plus D times I. There we have it. So that's now a complex number. This is the real part, right? And this is the imaginary part. Fair enough. So there we have it. That's how you add two complex numbers together, right? You just add their real parts together, and then you add their imaginary parts together, and that's your new complex number, right? The sum of those complex numbers. Okay. Any questions on that? Okay. And now before we do an example, I'll just show you the subtraction. Okay. So if I have A plus BI minus C plus DI instead, well, associativity, right? But don't forget you have to distribute this negative sign, right? So this is the same thing as A plus BI minus C minus DI, right? Commutativity, so this is the same thing as A minus C plus BI minus DI, right? And then A minus C is a real number. Factor an I out of these, we get B minus D times I, right? And so this is your real part, right? And this is your imaginary part. Okay, there we have it. That's how you subtract two complex numbers. Any questions on that? Okay. See, I'll try to keep this up here. Now let's do some examples. And I'll just say perform the indicated operations. Perform the indicated operations. So for part 1, or I'll say for part A, let's do 5 minus 11i plus 7 plus 4i. Okay. So we can drop all the parentheses because of associativity, right? So we have 5 minus 11i plus 7 plus 4i, right? Now we can do commutativity, so we can say this is the same thing as 5 plus 7 minus 11i plus 4i, okay? Now 5 plus 7 is just going to be equal to 12, and I have negative 11 copies of I plus 4 copies of I, right? So that's just going to simplify to be negative 7 copies of I, right? So we have 12 minus 7i, okay? Any questions on that? Any questions on that at all? I'll scroll up a little bit there. All right, good. So then now let's go on to part B. And let's say we do, how about negative 5 plus I, and we're subtracting from that about negative 11 minus 6i. Okay. So we can drop the parentheses, but don't forget you have to distribute the negative sign here, right? So we have negative 5 plus I plus 11 plus 6i. Okay. So now having that, we can switch things around. So it's negative 5 plus 11 plus I plus 6i. Negative 5 plus 11, that's just 11 minus 5, which is 6, right? I plus 6i just means you have 7 copies of I now. So we get 6 plus 7i. Okay. That wasn't so bad, right? Addition and subtraction are pretty easy with complex numbers. Yeah. Multiplying complex numbers, it's not that bad either. Yeah. So that's going to be our next operation here. Multiply. Okay. So let's say that we had a complex number a plus bi, and we just want to multiply this by c plus di. Okay, so we have two binomials that we're multiplying together, right? Yeah. And anytime that you have binomials being multiplied together, you remember FOIL, right? Yeah. And foiling really is just a distributive law. That's all it is. Yeah. It just that multiplication distributes over addition. So everything gets multiplied by everything. So I'm going to have to multiply a by c, but I'm also going to have to multiply a by di, right? I'm going to have to multiply bi times c, but I'm also going to have to multiply bi by di, right? Okay. So let's do the red first. I have a times c, right? Plus a times di. Okay. That's a times that stuff. Plus, now I have to do b times I times c, right? So doing the blue now. So I'm just going to write that as BCI, right? Just in alphabetical order. And then with the I coming last, just canonical form is all it is. Okay. And then now we have b times I times d times I. So that's b times d times I squared, right? Any questions on that? I'll pause here for a second, actually. Yeah. Might have been a while since we've done any kind of foiling. Yeah. So let's just pause and make sure we understand everything that I did there. Okay. So now we have to kind of simplify this. So I have a times c here. I have ADI plus BCI. But if you recall, I squared is the same thing as negative 1, right? So I have that in my definition at the very top, right? I is the square root of negative 1, which is equivalent to saying that I squared is negative 1. So this is just b times d times negative 1. So this is the same thing as just subtracting b times d. Right? It's a real number. It's a negative real number, right? Or it could be positive depending on if b is positive or negative or d is positive or negative, right? Yeah. In any case, now I can use commutativity to say that this is the same thing as AC minus BD plus ADI plus BDI. And then now, this is a real number, AC minus BD. I could factor the I out of this, and we get AD plus, oops, I miswrote something. Sorry, everybody. This right here is BCI. Yeah, BCI. Okay. So now I can factor the I out of that, and I get AD plus BC times I. Okay. And so this is my real part, and this is my imaginary part. Okay. So any questions on that? So that's how we multiply complex numbers. Okay. So let's do an example on that. All right. So here's my example. Let's say we have 2 minus I, and we're trying to multiply that by 7, or sorry, 3 plus 7I. Okay. I'm just going to follow all the same steps I did above, right? I'm going to do 2 times everything here. So I'm going to get 6 plus 14I when I do 2 times this, right? And then I'm going to do negative I times this stuff. So I'm going to get a minus 3I and then plus a 7I squared, sorry, minus a 7I squared, right? Any questions on that? Okay, now I'll simplify a little bit. So this is 6 plus 14I minus 3I. I squared is the same thing as negative 1, so I have negative and negative. This becomes plus 7. Okay. I'll use my commutativity here to say this is the same thing as 6 plus 7 plus 14I minus 3I. Well, 6 plus 7 is just 13, and 14I minus 3I will be the same thing as 11 copies of I left over, right? So we get 13 plus 11I. Okay. Any questions on that? Any questions on that at all? Okay. So now that we have that, right? Let's see. I'll kind of break this up into 2 parts, right? The next operation we're going to talk about is division, of course. But I'm going to talk about dividing by a real number first. Oops, not a red number, a real number. Okay. So let's say we have A plus BI divided by C. Yeah. Okay. Now, remember division is the same thing as multiplying by the reciprocal. So if I divide by C, it's the same thing as multiplying by 1 over C. Right? And I like to express it that way, right? Because we are all familiar with the distributive property. Multiplication distributes over addition, right? So this is the same thing as 1 over C times A, which would be A over C, plus B times I divided by C, right? So I'll write that as B over C times I, okay, like that, okay? Fair enough, just using my distributive property, that's what we get. So if I'm dividing a complex number by a real number, it's not bad at all, right? Okay. Fair enough. So any questions on that? Yeah, so dividing by real numbers, easy, right? We love real numbers, okay? On the other hand, if I have, oh, yeah, and I said dividing by a real number here, so I can just kind of say dividing, get rid of that part, yeah. A plus BI divided by C plus DI. So now I have a complex number divided by a complex number. That's much more challenging, okay? That's a lot more challenging. We know how to divide by real numbers, but how do we divide by C plus DI, right? Okay, so here's what we can do. And this requires a definition. Okay, so here's my definition here. The complex conjugate of a complex number A plus BI, right, is A minus BI. Yeah. So I just changed the imaginary part of it to be negative what it was before. Okay. All right, so let me write that down. I.e., change the imaginary part only, right? Only to be negative what it was before. Okay. Now B could be a positive or a negative number here, right? So the complex conjugate of that could be then the positive version of that, right? So whatever B is, you're multiplying it by -1 essentially, right? So these are complex conjugates of each other. Complex conjugates of each other. Called a complex conjugate pair. Complex conjugate pair. Okay. All right, so complex conjugates always come in pairs. Yeah. Okay. So here's a shorthand notation that we use in, I think, pretty much every textbook for complex conjugates, right? We write that A plus BI, the complex conjugate of that, that's what this bar above it means, is equal to A minus BI. Yeah. Yeah. And since they're complex conjugates of each, since they are complex conjugates of each other, that means that A minus BI, the complex conjugate of that, is equal to A plus BI. Right? Fair enough. Okay. So why do we care about complex conjugates, right? I mean, this is an operation that we can do, sure, but what use is it, right? Anytime we multiply a complex number by its complex conjugate, we obtain a real number. So if I take any complex number and I multiply it by its complex conjugate, I always get a real number out. And so I'm going to demonstrate that now. A plus BI times A minus BI, right? I got to FOIL it out. So I got to do A times this. So I get A squared minus ABI. And then I got to do BI times this. So I get plus ABI. And then minus B squared I squared, right? Now, you're going to notice that this minus ABI and this plus ABI, they're going to cancel off, right? So I have A squared, and then I squared is -1, right? Yeah. So this is minus B squared times -1, which is the same thing as plus B squared. Yeah. So I multiplied a complex number by its complex conjugate, and what I got was the real part squared plus the imaginary part squared. That always works. Okay. So any questions on that? This is just a horrible building. Yeah. Yeah. Even if things weren't falling apart, it's still like just too hard to find anything. All right. So now that I have that, right? So I'm going to use that to be able to define how to do division by complex numbers. Okay. So let's go back up to here. We have A plus BI over C plus DI, right? And I'm going to say, let's move that down here. Okay. So A plus BI. Try to write a little bit neater than that. A plus BI divided by C plus DI. Okay, now I can multiply anything by 1, right, without changing the value of the fraction, right? Yeah, so I can say, well, this is the same thing as A plus BI over C plus DI times, well, here's 1 in a funny way. C minus DI divided by C minus DI, right? Okay, I could do that, no problem. And I know how to multiply fractions, right? So you just multiply the numerators. So we have A plus BI in the numerator times C minus DI in the numerator, right? And then I multiply the denominators. So I have C plus DI in the numerator times C minus DI. Oh, sorry, in the denominator times C minus DI in the denominator. Okay. So I've multiplied c plus di by its complex conjugate here in the denominator. Now I can show all the steps again, right, of how you multiply them together and we get a real number out of it, right? But remember, if you ever multiply a complex number by its complex conjugate, you just get the real part squared plus the imaginary part squared, right? So you're just going to get c squared plus d squared after multiplying those out, right? Okay, you don't need to show me that work. C plus di times c minus di will definitely be equal to c squared plus d squared. Okay. Yeah. So any questions on that? Okay. Well, let's see what we get up top then, right? Now, c squared plus d squared is a real number, so that's great because we know how to divide by real numbers. Let's see what we get on top, right? We have a times c minus ADI, right? And then we get plus CBI or BCI, I'll write it. And then minus BDI squared. Okay. All right. So then this is the same thing as AC minus ADI plus BCI. I squared is -1, so this is plus B times D now. Okay. And then the bottom is still C squared plus D squared, right? All right. And then now I can use commutativity here, right? So then we have AC plus BD minus ADI plus BCI, all divided by C squared plus D squared. Okay. And then now, right, in the numerator here, right, my complex number in the numerator will just be AC plus BD is the real part. Factor an I out of this, so I'm going to get plus a BC minus AD times I. I can write it that way, right? All divided by C squared plus D squared, right? Okay. Now remember, C squared plus D squared, that's a real number, right? So it's the same thing as multiplying by 1 over the real number. So then this is going to be the same thing as AC plus BD divided by C squared plus D squared plus BC minus AD divided by C squared plus D squared times I. Okay, so I'm distributing that to each one of those terms, right? Division distributes over addition, right? Now, this is the real part of your complex number. And this is the imaginary part of your complex number. Fair enough. Yeah. And it looks awful. Okay. That's a lot of work. Yeah. Let's do an example. Let's do a quick example here. We have just enough time to do an example. Okay. So let's say I have, how about 2 minus I divided by 3 plus 2I? Yeah. Okay. So I'm going to follow all those same steps I did above, right? I need to get a real number in the denominator. So in order to do that, I need to multiply by the complex conjugate. But whatever I do to the denominator, I got to do the same thing to the numerator, right? In order to preserve equality, right? Because I can only multiply things by 1, right? Fair enough. So there's me multiplying by 1 in a funny way. Okay, I'm going to simplify my numerator here. So I have 2 times I times 3 minus 2I. In my denominator, I have 3 plus 2I times 3 minus 2I, right? Okay, so that's what we have so far. Okay, so in my numerator there, I have, let's go ahead and FOIL it out. So 2 times 3 is 6, right? Minus 4I, right? I have this minus I times 3, so I'm going to get minus 3I, right? And then I have minus I times negative 2I, so it's going to be a plus 2I squared, right? In the denominator here, right? You don't have to FOIL it out, but you can if you want to. You're just going to get 3 squared plus 2 squared. Yeah, if you FOIL it out. Yeah. I'm going to bring that back here. Okay. So I'm going to write this 2 minus I over, 2 minus I times 3 plus 2I. Right now we have this mess, right? So this is 6 minus 4i minus 3i plus 2i squared, all over 3 squared plus 2 squared. And now I'm going to simplify it. Okay. So in the numerator, that's the same thing as 6 minus 4i, oops, minus 3i. Slowing down here. Okay. Minus 3i, and then plus 2i squared is the same thing as minus 2, right? Because I squared is negative 1. Downstairs, we just have 9 plus 4, which is just 13, right? So in the numerator, I have 6 minus 2 will be 4. Minus 4i minus 3i is minus 7i. And this is all divided by 13, right? And then now division distributes over differences, right? So this is the same thing as 4 divided by 13 minus 7 divided by 13 times I. Okay? So 4 over 13 is the real part of my complex number. 7 over 13 is the, sorry, negative 7 over 13 is the complex, the imaginary part of my complex number, right? Fair enough. Don't forget that negative sign, right? Okay. Now, it's important that you express all of your answers in standard form because they're going to ask for it in standard form, okay? Let's say that you wrote 4 over 13 minus 7i over 13 as your final answer. I think MyLab Math will count this wrong. Yeah, fair enough. Yes, it's technically equivalent to what we have over here, but you see that my I is pulled out over here, right? Yeah, I want a real number plus a real number times I, right? So that's the standard form. So this is what you want, okay? And I'm pretty sure MyLab Math will mark it wrong otherwise, okay? Just to let you guys know.